To build smaller, efficient AI models, the industry relies on a process called knowledge distillation. The goal is to extract the predictive power, the dark knowledge, from a massive, cumbersome neural network and transfer it into a lightweight replica. The standard method for this transfer involves feeding identical data to both networks and comparing their output probabilities. This comparison uses the Kullback-Leibler, or KL, divergence loss function. Raw network logics pass through a softmax function, converting them into a softened probability distribution. KL divergence acts as a bridge, calculating a penalty whenever the student's probabilities deviate. The machine learning community relies on a specific methodology to tune this loss function. However, mathematical proof demonstrates that this default tuning strategy is actively bottlenecking student model performance. Deploying high-performance, edge-capable AI requires pristine knowledge transfer. The tool we default to for that transfer is inadvertently corrupting the signal. The softness of those probabilities is controlled by a hyperparameter called temperature scaling, represented by the Greek letter tau. As tau approaches 0, the distribution sharpens into a single spike. This label matching teaches only strict right or wrong answers. Scaling the temperature up flattens the curve, revealing nuanced probabilities of incorrect classes. This logic matching transfers structural relationships, providing deeper understanding. Empirical testing consistently verifies that models achieving logic matching generalize better to unseen data. Because of this, the accepted professional assumption is simple. Crank the temperature parameter to infinity, assuming KL divergence will perfectly match the raw logits. This assumption is a mathematical illusion. When tested, high-temperature KL divergence fails to perfectly match the teacher's logits. Relying on temperature scaling to force KL divergence into logit matching creates an invisible ceiling on the student model's potential. To calculate the formal limit of the KL divergence gradient as tau approaches infinity, the equation expands into two parts. The first half calculates the mean squared error between the logits, but the expansion reveals a critical flaw, a hidden secondary regularization term, delta infinity. For perfect logit matching to occur, this delta infinity term must equal exactly 0. Mathematically, that only happens if the mean of the logits for both the teacher and the student is exactly 0. Researchers at KAIST analyzed empirical data to test if this zero mean assumption holds up during actual model training. This chart shows the distribution of the teacher model's logit sums. The distribution is incredibly tight and centered almost perfectly at 0, satisfying the first half of the condition. This second graph shows the student model's logit summation as the temperature parameter tau scales up. As the temperature scales to 100, the student's logit mean drifts aggressively. The purple distribution is pushed wildly far from the 0 mark. During training, the optimization process actively forces delta infinity to shift the mean of the student's logits. This pulls the student's internal values out of alignment with the teacher. Attempting to match logits using KL divergence fights the underlying math. The optimization process itself generates an artifact that sabotages the knowledge transfer. The solution to the delta infinity artifact is straightforward. Bypass the softened probability distribution entirely. By calculating the mean squared error directly between the logit vectors of the two models, the delta infinity artifact is completely removed from the optimization process. To prove that direct mean squared error transfers knowledge better, we have to look past the final output probabilities. We need to examine the latent space, the geometric layout of the network's penultimate layer representations. This scatter plot displays the latent space of the teacher network. Notice the distinct cohesive geometry, where different classes form tight, well-separated clusters. This next chart shows the latent space of a student model, learning that geometry using a high-temperature KL divergence loss. The student forms clusters, but they are elongated and diffuse, failing to capture the tight structural cohesion of the teacher's original network. Now, this final scatter plot shows the representations of a student trained using direct mean squared error on the logits. The structure here is much tighter. The clusters accurately replicate the strict geometric boundaries established in the original teacher's plot. Applying mean squared error directly to the logits physically structures the student's internal latent space to match the exact geometric understanding held by the teacher. If direct mean squared error creates a geometrically superior student, it raises a logical question. Why should a distillation pipeline ever use KL divergence? Perfect logic matching possesses a fatal vulnerability. If the original training data contains corrupted, incorrect labels, it creates a noisy teacher scenario. In this environment, mean squared error is too precise. If a poorly fitted teacher makes a highly confident error on a bad label, direct MSE forces the student to perfectly memorize that mistake. This chart maps test accuracy when 40% of the training labels are randomized noise. On the right side, the dashed green and blue lines represent direct MSE and high-temperature KL divergence. Both suffer severe drops because they flawlessly transfer corrupted noise. Look at the peak of the solid blue line on the far left. The maximum accuracy in a highly noisy environment is achieved using KL divergence at a very low temperature, a tau of 0.5. A low-temperature KL divergence ignores the relative structural relationships between logits. It acts as a regularization buffer, prioritizing blunt label matching and shielding the student from the teacher's confident errors. High-fidelity knowledge transfer is dangerous when the source material is flawed. A noisy environment requires a loss function that filters data rather than copying it perfectly. This leads to a definitive decision framework for designing distillation pipelines. If the training dataset is clean and the teacher model is highly accurate, bypass KL divergence. Apply direct mean squared error to the logits to maximize geometric alignment and overall generalization. If the dataset suffers from noisy labels or the teacher is poorly fitted, use KL divergence with a low temperature to block the transfer of corrupt confidence. True model optimization requires understanding the mathematical artifacts hiding inside the latent space, allowing engineers to choose the exact right tool for their data environment.